Hello students, welcome to the course of Organic Chemistry Chem 322. Today we will be discussing the E2 elimination reactions. Previously we have discussed the E1 elimination reactions, and now today we will be going to the E2 elimination reactions in detail. What the topics we will be discussing in this lecture, that will be comprise the introduction to the E2 reactions, that what are the E2 reactions and how it proceeds in the process, and what will be the resultant compounds that are formed in the E2 reactions. Mechanism of the E2 reactions. How the E2 reactions proceeds, what are the conditions, and what are the requirements for the E2 reactions. Orientation of the double bond. In the elimination reaction, there is the formation of a double bond. That double bond can be formed in different locations, and we will be studying the orientation of the double bond, that which one will be the most probable position at which the double bond will be created after the E2 reaction, and effect of the conditions on the rate and mechanism of reaction. There are different conditions associated with the reaction. That might be the temperature, that might be the solvent, that may be the base or the nature of the base, which can affect the rate of a reaction and the mechanism of a reaction. So we will be discussing these conditions in detail, that what are those conditions which can favor a certain type of product in the E2 reaction. First, what is E2? E2 indicates an elimination reaction, bimolecular reaction. It is bimolecular reaction. It means that the rate determining step, or the rate is of two, directly proportional to the two molecules. The one is the substrate and the other one is the base. Here the substrate is the tertiary butyl bromide, and we have a base, the hydroxyl ion. That may be sodium hydroxide, potassium hydroxide, or any other base. And the product is 2-methylpropene, water, and bromide has left the molecule. The rate of an E2 reaction depends on the concentration of both tertiary butyl bromide and hydroxide ion. It is therefore E2 is a second order reaction. Like E1 was a first order reaction, the same is the case that E2 is a second order reaction, because there are two molecules, the substrate and the base, which are involved in the rate limiting step or rate determining step. Rate is like here, in this particular reaction, the rate will be proportional to the rate constant and the concentration of the substrate, that is tertiary butyl bromide, and the base. An E2 reaction is a concerted one-step reaction. That concerted means that one step is preceding the other step, or one step comes second after the other step, or all the steps are coming in the same one by one step reaction. The proton and the bromide ion, the leaving groups, are removed in the same step, so no intermediate is found. Like in the E1 reaction, there was the formation of an intermediate, that was the carbocation, and after the formation of carbocation, there was the removal of proton in the second step, and that was the rate determining step also. But in the E2 reaction, both the leaving groups leave the molecule in the same single step, like here. This is the mechanism of the E2 reaction. A proton is removed. This is the proton, which is removed by the base. Here, this bond migrates to, these electron migrates to this bond with the other carbon, and the bromine is eliminated, and we have a double bond here between these two carbons. So this is the mechanism of the E2 reaction. In the E2 reaction, the electrons that were bonded to the hydrogen in the reactant have formed a pi bond in the product. Like if you see in the previous slide that the proton was removed by the base and the electron migrated to the bond between the two carbons, and it make a pi bond in the product. In an E2 reaction, there is one step which is also the rate determining step, and there is no intermediate formation. As all the steps are simultaneous to each other, so there is no intermediate formation, as was the case in the E1 reactions, the formation of carbocation, that was an intermediate in the E1 reaction. But here in the E2 reaction, there is no formation of intermediate, and the one step reaction is, that is the rate determining step also. E2 reaction, it is also called elimination bimolecular. Why? Because E2 reaction takes place in a single step, and the base and hydrogen single bond and the carbon-carbon double bond, that is, one is the single sigma bond and the other is the pi bond, formed at the same time, that the CH sigma bond and the Cl sigma bond break. So the formation of the base and the hydrogen sigma bond, like here, this is, and the formation of the carbon-carbon double bond here, this one, and that occurs at the same time when the CH sigma bond, this one, and the carbon and the leaving group, this one, that bond breaks at the same time in the same step. So it is a bimolecular reaction. The base in an E2 step is the electron-rich species, but the hydrogen atom that the base attacks is not particularly electron-poor. Instead, the electron-poor atom is the carbon atom bonded to the leaving group. If you see here, base, it's an electron-rich species. This is an electron-rich species. This electron-rich species attacks the proton. But if you see the hydrogen, it is not an electron-deficient species or electron-poor species. But if you look at here, there is a partial charge on the carbon. So what does it mean? That this carbon is electron deficient or electron poor. And which carbon is electron deficient? To which the leaving group is attached. This carbon is electron deficient because here the leaving group is attached. Why? Because the leaving group is electronegative, more electronegative as compared to the carbon, and it attracts the electron towards itself. So the movement of electrons from the electron rich side to the electron poor side is depicted with two curved arrows originating from the strong base. Like this deficiency or this movement of electron from electron rich to electron deficient is here. Like the electron moves here, it attracts the proton, not the hydrogen. It takes the proton. The electron of the hydrogen that migrates to this carbon, and the leaving group leaves this molecule along with the electrons. These are the curves and these are the resultant molecule, and at the end we have a neutral base and we have these carbon-carbon pi bond and the electron rich leaving group. So the E2 is concerted and takes place in a single step. The formation of the base and the hydrogen sigma bond and the formation of carbon-carbon double pi bond form at the same times that the carbon-hydrogen sigma bond and the leaving group and the carbon sigma bond breaks. The attacking species is a Bronsted base which abstracts a beta hydrogen to the leaving group. That base attracts the hydrogen which is beta to the leaving group. Like here, it is the leaving group, and the carbon to which the leaving group is attached is the alpha carbon, which is beta carbon, and the hydrogen attached to the beta carbon is the beta hydrogen. So, and at the result, there is the formation of double bond between alpha and beta carbon. E2 reaction. The carbon to which the halogen is attached is called the alpha carbon. A carbon adjacent to the alpha carbon is called a beta carbon, as we have discussed in the previous slide. Because the elimination reaction is initiated by removing a proton from a beta carbon, an E2 reaction is sometimes called a beta elimination reaction. It is also called a 1,2 elimination reaction because the atoms being removed are on adjacent carbons. It is also called 1,2 elimination because if we consider the carbon to which the leaving group is attached as 1, so the adjacent carbon is the 2, and the hydrogen is removed from the adjacent carbon, so it is called a 1,2 elimination reaction. In a series of alkyl halides with the same alkyl group, alkyl iodides are the most reactive and alkyl chlorides are the least reactive in E2 reaction. This is the relative reactivities of the alkyl halides. Alkyl iodide is the more reactive, then comes the alkyl bromide, then comes the alkyl chloride, and the alkyl fluoride is the least reactive because the fluorine group has a high electronegativity and it is very much tightly bonded to the carbon species. The weaker is the base, the better is the leaving group. So the more is the E2 reaction favored. The weaker is the base. Here, iodide. The better is the leaving group. So how much it is weaker, it will be a better leaving group. And the more is the E2 reaction favored. And it will favor the E2 reaction. Rate law of the elimination reactions. Like 1 bromo, 1 dimethyl ethane, it will form a 2-methyl propane. This is an example of the E2 reaction. and the rate law will be 1 bromo 1 dimethyl ethane and the concentration of base. This is a classic elimination reaction we are forming here. The classic elimination reaction, we are forming a new CC pi bond and breaking a CH and a C leaving group. Here is the bromine. This is the base, sodium methoxide in the presence of methanol, and it forms a double bond here, and is the formation of sodium bromide and methanol. Form CC bond, pi bond, break CBr sigma bond. Form OH sigma bond and breaks CH sigma bond. When will the E2 reaction occur? Elimination happens when the nucleophiles attack hydrogen instead of carbon. This is a difference between the elimination and substitution. In the substitution, the nucleophile attacks a carbon, while in the elimination, the nucleophile attacks the hydrogen. The strength of the base has a role in the rate of reaction, as it is involved in the rate determining step of the elimination, and so it appears in the rate equation. Here is the base is directly involved in the rate determining step, so the strength of base has a particular role in the reaction. When we increase the concentration of the substrate or the concentration of the base, the reaction rate increases accordingly. In other words, there is the first order dependence of the rate on the concentration of substrate and base, and second order overall. The overall reaction is second order, but there is a direct effect on the rate of the concentration of the substrate or the concentration of the base. This is like the reaction rate depends on the concentration of both base and substrate. First order in alkyl halide plus first order in base and second order overall. Doubling the concentration of the base doubles the rate of the reaction. Order of alkene stability. The stability of an alkene increases as the number of R groups bonded to the double bond carbons increases. What are the stability of the resultant alkenes which are formed as a result of the E2 reaction? So, greater are the number of alkyl groups or substitution on the double bond, more will be the stability. Like here, the ethene is the less stable, while 1122 dialkyl ethene is the more stable. The higher the percent S character, the more readily an atom accepts electron density. Thus, sp2 carbons are more stable to accept electron density, and sp3 carbons are more able to donate electron density. The sp2 carbons are more able to accept electrons because there is more S character in sp2 bonding or sp2 carbons, and the higher the percent of the S character, the more readily an atom accepts electron density, and the lower are the sp3 carbons, they are more electron donating. So, in increasing the number of electron donating groups on a carbon atom able to accept electron density makes the alkene more stable. Stability of Trans-substituted alkenes. Trans-2-butene, a disubstituted alkene, is more stable than cis-2-butene, another disubstituted alkene, but both are more stable than 1-butene, a mono-substituted alkene. Here, this is less stable. Then comes the disubstituted or 2-substituted. So the cis-2-butene is more stable as compared to the 1-butene. But the trans-2-butene, it is more stable than the cis-2-butene. This is the stability order. These are the characteristics of the E2 mechanism. Mechanism is one step. Identity of R, that is alkyl group. More substituted halide react fast. Base, the reaction is favored by strong bases. Leaving group, better is the leaving group, faster is the reaction, as we have seen in the case of the alkyl halides, that alkyl iodide is better leaving group, iodide is better leaving group as fluoride, and the reaction is favored from the alkyl iodide as compared to the alkyl fluoride. And solvent, it is favored by polar aprotic solvents. Thank you.